A warm welcome again here at the Industrial Vision Days to the next session about vision processing. Today we have 3 speakers here within this session, and we will start with Gion-Pitchen Gross, Director Product Management and Marketing from Allied Vision Technologies. And Gion-Pitchen Gross will speak about machine vision on embedded systems, possibilities and limitations. Gion-Pitchen, the stage is yours.
Thanks, Paul. A warm welcome from my side to everybody. Thanks for the introduction, Paul. I'm glad to be here. I'm glad that you are decided to spend your lunch break with me. I hope it will be worth it. So let's get started. What I'm going to talk about today, different things. So after a short introduction, I'll compare some computing systems, more a PC-based traditional machine vision system, and then a newer embedded vision system. In the next part, I'm going to compare some machine vision cameras, some GigE cameras, USB3 cameras, and also MIPI CSI-2 cameras. What are their specialties? How suited are they for embedded applications? And then in the next part, how to enable really machine vision on embedded systems. I have 3 things that we are working on and are actively doing to enable this more and more. And in the last part, I have a few performance measurements which we did on CPU loads, comparing some interfaces, and I'll finish with a short conclusion. But first, who is Allied Vision? Allied Vision has been an industrial machine vision and camera supplier for more than 30 years. We are now part, or we have been part of the TKH group for a long time, and we are now here presenting for the first time as TKH Vision, kind of our mother. As Allied Vision, we have roughly 250 employees, headquartered in Germany, in Thuringia, in Stadtroda. We do the camera hardware, we do the embedded software on the hardware, but we also do the host side to be able to control the camera. And we are not only doing visible light imaging, we are also, I would say, the market leader in shortwave infrared imaging, for example, SWIR. But also, of course, near-infrared cameras. We also do custom development for OEMs. So let's get started. Just a very basic sketch of a machine vision system. I'm sure you are quite familiar with it. So today I'm mostly focusing on the host PC part, where the image processing library sits, and also on the camera part. I will not touch the other parts of an embedded or of a machine vision system. So I mentioned I'll compare some computing system. So let's first start with a kind of a more traditional machine vision system based on an Intel Xeon processor. It's quite a new one, so it has 16 cores, kind of 2.2 gigahertz base frequency. There's no GPU directly on the board. Also, memory is not there. Very flexible. It has some USB3 connectivity. I think what stands out here is the Ethernet. The Ethernet that you have here, 4 times 10 GigE, so very well equipped in terms of Ethernet connectivity, and also in terms of PCI Express. There's many slots to choose from and expand the system. If we look at in terms of power, that's just the CPU. A thermal design power of roughly 100 watts. So what can we say about this? Well, we have quite some powerful cores here, many cores with quite high speeds. And it's a very general purpose design because it's expandable. You can use any type of GPU that you want. You are very flexible on the memory side. So it really has a very general purpose design that you can expand to your needs or adapt to your needs. Very high connectivity in terms of Ethernet, and then many expansion ports to really design the system according to your needs. I mentioned only the CPU uses roughly 100 watts. That won't be enough for the whole system, so we're well above 100 watts in terms of power consumption here. Now, if we compare this to a example embedded system. Here on the example of the Xavier NX from NVIDIA, we have a 6-core CPU at 1.4 gigahertz. We have an integrated GPU. We also have a fixed amount of memory here. In terms of USB connectivity, it's quite similar, I would say, but Ethernet here is much different than before, so we just have one GigE port here kind of on just there. In terms of PCI Express, there is PCI Express, but just 2 slots for expansion. Also there it's different. One of the main differences is really that this system offers direct camera connection capabilities from MIPI CSI-2, 12 lanes, so up to really 12 cameras can be connected to such a system, directly supported. And also a big difference here is in terms of power. We have 10 to 15 watt modes for the whole system on module. So to compare it, there's much less power here in terms of CPU, but there's already an integrated GPU and pre-installed memory. There's different versions of memories available, but not as flexible as in the system before. In terms of USB connectivity, it's quite similar, but it's only 1 GigE port, but the direct connectivity of up to 12 cameras, and much lower power than the system shown before. So again, to compare it, the first one, the kind of standard Intel Xeon system, very flexible, high-performance system, and other components can be added very easily via high-speed interfaces. It has a larger footprint, so it's not as small as the NVIDIA SOM, and it needs a lot more power. However, you're also very flexible on the operating system that you want to use on this board. You can use Windows or any types of Linux flavor that you want. Comparing this to the embedded system, the hardware configuration is pretty much fixed. You have a SOM that is available with 2 or 3 memory configurations. In terms of expansion, it's also not as flexible, but it's very small and it's very efficient. So it's really suitable for low power system. And in terms of operating system, it's not as flexible as before. It's really fixed to this L4T, Linux for Tegra, and needs to be used with that. So moving on to the cameras, if we compare some cameras, let's start with a standard machine vision camera based on a 1 GigE or GigE Vision interface. For example, shown here our Mako camera. In terms of interface connectivity, it's really everywhere. Every system, whether it's PC-based or embedded, has a GigE Ethernet port. It's really there. In terms of bandwidth, yeah, it's 1 GigE. So in terms of image data, it gives you roughly 110 megabytes per second throughput. It's well standardized in machine vision, so there's the GigE Vision standard, which is well established, has been used for many years. So also the feature side is very standardized and very advanced control features for the cameras are available. And also in terms of synchronization, there is a lot of options. There's, of course, the external signal synchronization via the I/Os, but there's also the precision time protocol, which can synchronize it directly via Ethernet cable. In terms of cabling, GigE is also very flexible. It can go up to 100 meters, and the cables are also widely available and very affordable. Comparing this to a USB 3 machine vision camera, also the USB 3 interface is very ubiquitous. It's almost the same as a GigE interface. It can be found everywhere. In terms of bandwidth, it offers a much higher bandwidth, so 5 gigabits per second theoretically. What we say is really usable is roughly 450 megabytes per second. We also have a well-established standard there, USB 3 Vision, and that also standardizes many advanced camera control features. Synchronization here is mostly via external signal, via the I/Os. In terms of cabling, it's also a bit different than GigE because it's not as flexible. The cabling is not so long. You can get standard copper cables maybe up to 8 meters. Yes, there's active optical cables which can expand this to much larger lengths, but they're also quite pricey, I would say. Let's look at the third camera here on the block. That's a CSI-2 embedded camera. In terms of interface connectivity, the situation here is a bit different. So it's mostly focused on ARM-based systems running Linux. Also on the connector side, it's not a standardized, so there's no standard connector currently. There is a quasi-standard, more or less, which comes from the Raspberry Pi. They have been kind of popularizing that interface, so many boards use the Raspberry Pi connector. However, it's not standardized, not everybody's using it. Also, our cameras are using a different connector. In terms of bandwidths, there is quite a few CSI-2 standards. The one we're using in our camera is D5 version 1.1. Gives you up to 1.5 gigabits per lane, up to 4 lanes, so theoretically 6 gigabits per second. What we're currently using, I mean, they're still in optimization phase, is roughly 520 megabytes per second. But as I said, that's still in the optimization, and much more is actually possible. In terms of standardization, here it's also a different picture. It's not standardized. We heard before, there's a standard in preparation, and there is a kind of a standard or a framework that's available from the Linux side, which is the V4L2, Video for Linux 2 Inter or framework, that's available, and it just defines some very basic camera control. In terms of synchronization, what can be done is also here. We have 2 GPIOs, which can be used for synchronization with an input and an output. Cabling is based on FPC cables, so the flat band cables. They're quite limited. We offer them up to 40 centimeters, but there's now also the serializer, deserializer interfaces. There's FPD link or GMSL, and those use then coax cables, which can go up to 15 meters, and I will touch on this a little bit later in more detail. So if we compare them again, the 3 different interfaces which I introduced, it's kind of the GigE is the most robust and ubiquitous really on the market, and USB 3 has also been quite widely used in the industry in the past years. MIPI CSI-2 is a bit different. It's really a fast and specialized interface. In terms of bandwidth, GigE is limited. USB 3 provides medium bandwidth, I would say. It's always a matter of perspective. I mean, we have here other companies who offer up to 100 gigabits per second, but for us, we call it medium with 5 gigabits per second. And MIPI CSI-2 is a bit higher with up to 6 gigabits, but as I mentioned, there's still an optimization process ongoing. Standards, well established on the GigE and USB 3 side, still in preparation for CSI-2. Also in terms of features, many features on GigE and USB 3, and only basic features currently on CSI-2. Synchronization, quite similar. Biggest difference is again in the cabling currently, with GigE having up to 100 meters, USB 3 up to 8 maybe with normal copper cable, and then short cables for CSI-2. So what can we really do to enable machine vision on embedded system more in the future? I have 3 points here to make. The first one is what we do is we try to make machine vision cameras more suitable for embedded. So what we offer is we offer very small board level based on USB 3 and CSI-2. So they're better and easier to integrate in small spaces, which are often the case when using an embedded system. Also, we are planning to enable different connectors to be used with USB 3 cameras. That's also sometimes the wish from customers, so we will have this available quite soon. Also, because embedded systems are usually low power, also we focus to make the cameras more low power, and also to offer features to even go beyond that and enable some power saving modes on the camera as well. And then on the other side, on the more embedded CSI-2 cameras, we are offering more embedded or more machine vision sensors to bring them together more. So the second thing we are doing is we really are working on longer and more flexible cabling for CSI-2. On the hardware side, that's been one point that's been holding it back. So by using those serializer, deserializer technologies, One is FPD-Link 3, the other is GMSL2. We can really enable longer and much thinner cables for CSI-2 cameras. Another thing is they use a very robust connector, which is also with the FPC connectors sometimes an issue because they are, can be quite fizzly. The third point is that the handling on the feature side, not many people in the machine vision industry are familiar with Video for Linux 2. So what we are working on is to make machine vision software available also on CSI-2 camera and to offer more advanced control features in the CSI-2 cameras. And we call this GeniCam for CSI-2. So we will provide a GenTL, a transport layer for our CSI-2 cameras to be used with other GeniCam compliant software, and it will also make it much easier to use CSI-2 cameras in machine vision applications. Okay, some short performance testing we did, I think very interesting. USB 3 versus CSI-2 on a Jetson TX2 embedded system. 3 different resolutions from 5 to 20 megapixel. So 5 megapixel rolling shutter sensor from onsemi, 12 megapixel global shutter from Sony, and 20 megapixel rolling shutter also from Sony, comparing the performance in terms of CPU loads on the TX2 system. So the 5 megapixel sensor, it achieves a maximum throughput of roughly 68 frames per second. We did 2 measurements, one with kind of half the speed, so 34 frames, and 68 frames. And if we look at the comparison is that, okay, CSI-2 creates a little bit less CPU load, but not that much. 3 to 7% lower CPU usage, that's already something. If we move on to a larger resolution, so here a 12 megapixel global shutter sensor, we see we reach 14 frames in CSI-2. We see much bigger difference in terms of CPU load. So we see that we have a difference in 16 to 80% lower CPU load on the CSI-2 side compared to USB 3. The same for 20 megapixel. Also here we have a much lower CPU load of 17 to 19% even. So when we conclude here, it's really the higher the resolution, the more advantage you have using CSI-2 in terms of CPU load. It creates much less load. And even at low bandwidths, we can say there is also some benefit, but it's not that considerable. So to conclude here, in terms of embedded systems, they offer some benefits to traditional PC-based systems. They're very small and efficient. However, they have limitations in terms of hardware and in terms of CPU power. If we look at on the camera side, and that's, I'm finishing, it's the last one. Sorry. On the camera side, we can say to make machine vision cameras better suited for embedded vision. That's what we're working on. We need more flexible cabling solutions. We need easier handling of CSI-2 cameras. And with the reduced CPU load that CSI-2 creates, it's also more suitable for embedded systems, which are not as powerful as traditional PC-based systems. Thanks for being here, thanks for watching, and I'm happy to take your questions.
Okay, ladies and gentlemen, since we have to take care about the time, I would kindly ask if there are any questions, please stay here and use the possibility to contact Gion-Pitchen Gross after this session. Unfortunately, here we have no time to go on with questions.